In the year 1970, something quietly revolutionary began to unfold in the temperature-controlled rooms of corporations and institutions around the world. IBM announced the System/370 line, a family of mainframe computers that represented what engineers called the third generation of computing machinery. These weren't the first mainframes, but they marked a turning point, a moment when computing power consolidated into sleek metal cabinets filled with integrated circuits and semiconductor memory, rather than the older, bulkier transistor arrays that had come before. The change was subtle from the outside. These machines still occupied entire rooms, still required raised floors for cooling systems, still hummed with a particular frequency that operations staff would grow to find comforting during long night shifts. But inside, at the level of electrons flowing through silicon, everything had transformed. The integrated circuits allowed these systems to process information faster, to hold more data in active memory, to handle more simultaneous tasks. And perhaps most significantly, they took up less physical space than their predecessors, though they were still enormous by any standard we might recognize today. This physical compression of power had consequences that rippled outward through the organizations that adopted these systems. When something becomes smaller but more powerful, when it shrinks while simultaneously expanding its capabilities, it changes how people think about it, how they deploy it, how they depend upon it. The early System/370 models found their most eager adopters in specific industries. Banks were among the first to embrace this technology with real enthusiasm. Airlines followed closely. Retail chains began to see the possibilities. What these sectors had in common was a structure, a geography of operations that the mainframe seemed uniquely suited to serve. They had central headquarters and scattered branches, main offices and remote locations, core operations and peripheral sites. The architecture of the System/370 line aligned perfectly with this distributed but centralized model. A single mainframe, sitting in a climate-controlled room at corporate headquarters, could serve dozens or even hundreds of remote terminals scattered across cities, states, or countries. Each branch office, each ticket counter, each retail location could have its simple terminal, its green glowing screen and clacking keyboard, while all the actual computing power resided elsewhere, hidden, centralized, operating in a silence broken only by the whisper of cooling fans and the occasional chatter of a line printer. This created a peculiar dynamic. Thousands of workers would come to depend on these systems for their daily tasks, typing data into terminals, retrieving records, processing transactions. But the machine doing the work was somewhere else, often in a building they'd never visited, in a room they'd never seen, operated by technicians whose names they didn't know. The power was centralized, the dependence was universal, and the understanding was fragmentary at best. In the 1970s, acquiring a mainframe represented one of the largest capital expenditures most organizations would ever make. The cost was extraordinary, measured in millions of dollars, a sum that demanded approval at the highest executive levels and often required special financing arrangements. This wasn't like purchasing office equipment or even factory machinery. This was an investment that would shape the organization's capabilities for years, perhaps decades to come. The expense created pressure, an economic imperative that influenced every decision about how these machines would be used. If you've spent millions on a single computer, you cannot let it sit idle. You cannot afford to have it serve just one department or handle just one application. The economics demanded that these machines be shared, that their processing power be divided among many users, many departments, many purposes simultaneously. This sharing was accomplished through sophisticated operating systems, software that could juggle dozens of programs at once, allocating processor time in tiny slices, creating the illusion that each program had the machine to itself when in reality all were taking turns, one after another, in rapid succession too fast for human perception to detect. The technical term was time-sharing, and it worked beautifully from an economic standpoint. But it also meant that no single person or department truly controlled the machine. Everyone shared it, everyone depended on it, and everyone had to adapt their work to its rhythms and requirements. Because these mainframes ran continuously, because stopping them meant stopping everything they supported, because every hour of downtime represented lost productivity across entire organizations, a particular culture developed around them. These machines ran 24 hours a day, 7 days a week, with downtime scheduled only for essential maintenance and carefully planned in advance. In this environment of constant operation, experimentation became dangerous. If a program behaved strangely, if a transaction processed in an unexpected way, if data appeared or disappeared without clear explanation, the instinct wasn't to stop everything and investigate thoroughly. The instinct was to work around it, to note it, perhaps to mention it to colleagues, but rarely to dig deep into root causes unless the problem was catastrophic and recurring. This created a strange folklore around these systems, collections of unexplained behaviors that operators and programmers learn to accommodate rather than understand. The system always runs slowly around 3 in the morning. Don't submit that job type on Fridays. That error message doesn't mean what the manual says it means. These became institutional knowledge, passed from one shift to another, from senior staff to newcomers, accepted truths that might or might not have solid technical foundations, but that everyone learned to live with. The machines acquired personalities, quirks, mysterious characteristics that made them seem almost alive in their unpredictability. For the vast majority of people who interacted with these mainframes, the experience was mediated through terminals. These weren't computers themselves, just devices for communicating with the distant, powerful machine. The interface was almost always text-based, character-based, built around forms that users would fill in field by field. The screens glowed green, or sometimes amber, with letters and numbers appearing in fixed positions, carefully aligned, each character occupying its predetermined space in a grid. These interfaces seemed simple, almost crude. Type a customer account number here. Enter a transaction amount there. Press enter. Wait. The screen clears. New information appears. Simple. Direct. But behind that simplicity, invisible to the terminal user, complex logic executed on the mainframe. The account number you typed might trigger dozens of validation checks, database lookups, cross-references with other systems. The amount you entered might pass through transformation routines, currency conversions, authorization hierarchies. All of this happened on the host system, in code the terminal user never saw, following rules they might not fully understand. This separation between the simple interface and the complex processing behind it created another layer of mystery. Users knew what they needed to do, knew which fields to fill and which function keys to press, but the how and why remained opaque, happening somewhere else, in that climate-controlled room, in that humming machine they'd never seen. Access to the deep knowledge of how these systems actually worked was carefully controlled. Not everyone could write the programs that ran on mainframes. Not everyone could modify the operating system, or install new software, or change system parameters. These privileges were restricted to systems programmers, a small elite group whose specialized knowledge made them indispensable and powerful within their organizations. This concentration of expertise was partly practical, partly necessary. These systems were complex, and mistakes at the systems level could be catastrophic. But it also created knowledge silos, small groups of people who understood the machines, while everyone else remained dependent users. The systems programmers developed their own culture, their own language, their own ways of thinking about problems. They worked odd hours, were called in for emergencies, held the keys to the kingdom in a very literal sense. The operational rhythm of organizations with mainframes began to revolve around a particular pattern. a daily cycle that became almost ritualistic in its predictability. During business hours, the mainframe handled interactive work, supporting all those remote terminals, processing transactions as they occurred, responding to queries in real time. But at night, when the terminals went quiet, when the branch offices closed and the transaction volume dropped, the mainframe's work was just beginning. Overnight batch processing became the heartbeat of mainframe operations. All day long, transactions would accumulate, changes would be recorded, temporary files would grow. Then, in the quiet hours after midnight, the batch jobs would run. These were programs designed to process everything that had accumulated during the day, to update master files, to generate reports, to reconcile accounts, to prepare data for the next business day. Entire workflows were structured around this rhythm. Reports couldn't be generated until the overnight processing completed. Month-end closing stretched across multiple nights of batch processing. Year-end might require a full weekend of computational work. Organizations adapted, planning their activities around what the machine could do and when it could do it. The mainframe schedule became the organization's schedule. Through all of this, through the expensive hardware and the careful scheduling and the elite programmers and the mysterious behaviors, something profound was happening. These mainframes were becoming trusted authorities, the definitive sources of truth for their organizations. If the mainframe said an account balance was a certain amount, that was the balance. If it calculated that inventory levels had dropped below reorder points, those orders were placed. If it determined that a credit application should be declined, it was declined. This trust developed gradually, transaction by transaction, day by day, as the systems proved themselves reliable even when they weren't fully understood. Most users, most managers, most executives had no deep comprehension of how these systems actually worked internally. They couldn't have explained the operating system architecture, or the database management techniques, or the transaction processing protocols. But they trusted the results, trusted the outputs, built their decisions and their businesses on data these machines produced. This trust before understanding created a particular relationship between humans and computers, one where reliability mattered more than transparency, where consistent results were valued more highly than comprehensible processes. If the system worked, if it kept working, if it produced the right answers day after day, year after year, the how became less important than the that. And so a foundation was laid, a pattern was established, for computing that was powerful beyond anything previously imagined, centralized in ways that concentrated both capability and control, and quietly inscrutable to most of those who depended upon it. The mainframe era of the 1970s created technology that organizations couldn't function without but that they couldn't fully explain, systems that became embedded in operational DNA, even as their inner workings remained mysterious. This was the beginning, the first generation of truly centralized corporate computing, and its legacy would echo forward through decades, shaping assumptions about technology, control, and trust that persist even now, long after these particular machines have been retired to museums and the memories of those who operated them. The silent code of the 1970s mainframe was powerful, essential, and ultimately, to most who depended upon it, unknowable. In 1972, IBM announced an enhancement to the System/370 line that would fundamentally alter how programmers thought about memory, or perhaps more accurately, how they stopped thinking about memory in certain ways. This was the introduction of full hardware-supported virtual memory, a feature that would become so standard in computing that later generations would assume it had always existed. But in that moment, it represented a profound shift, a new layer of abstraction between what programs requested and what the hardware actually provided. To understand why this mattered, we need to consider what came before. In earlier systems, memory was concrete, physical, and strictly limited. If a machine had 2 megabytes of RAM installed, that was all the memory available. Programs had to fit within that space, and programmers spent considerable effort organizing their code to squeeze into available memory. They knew exactly where each piece of their program resided, which addresses held which data. Memory was tangible, mappable, real. Virtual memory changed this relationship entirely. With virtual memory, a program could be written as if vast expanses of memory were available, far more than was actually installed in the machine. The program would reference memory addresses that existed in a logical space, a virtual addressing scheme that didn't directly correspond to physical RAM chips. The hardware, working in concert with the operating system, would handle the translation between virtual addresses and physical locations, managing this mapping invisibly, constantly, without the programmer's awareness or intervention. This was liberating in many ways. Programmers could write larger programs, could structure their code more naturally without constantly worrying about memory constraints. Multiple programs could run simultaneously, each believing it had access to the full memory space, unaware that they were sharing physical RAM through this virtualization layer. The system handled the complexity, managed the resources, made it all work. But this liberation came with a cost, a trade-off that wouldn't become fully apparent until these systems had been running in production environments for months or years. The cost was visibility, or rather the loss of it. Programmers could no longer see, could no longer directly control, how their programs actually used physical memory. The machine made decisions on their behalf, decisions that were usually good, but sometimes mysterious, occasionally problematic, and always invisible. The mechanism that made virtual memory practical was called paging. Physical RAM was divided into fixed-size chunks called page frames, typically 4 kilobytes each. A program's virtual memory was similarly divided into pages. When a program ran, only some of its pages needed to be in physical RAM at any given moment. The currently executing code, the data being actively processed, the stack frames of active function calls, these needed to be resident in real memory. But code that wasn't currently executing, data that wasn't currently being accessed, historical information that might be needed later but wasn't needed now, these could be moved out. When memory pressure increased, when physical RAM became scarce, the operating system would select pages to evict, writing their contents to disk storage and marking those physical page frames as available for other uses. This happened automatically, continuously, guided by algorithms that tried to predict which pages would be needed soon and which could safely be moved out. Most of the time, these predictions were accurate enough that programs ran smoothly, unaware of the constant shuffling happening beneath them. But sometimes, a program would try to access memory that had been paged out. The virtual address was still valid, still part of the program's logical address space, but the corresponding data wasn't currently in physical RAM. When this happened, the hardware would generate what was called a page fault, a special interrupt that paused the program's execution while the operating system retrieved the needed page from disk, found a physical page frame to put it in, possibly evicting another page to make room, updated the memory mapping tables, and then allowed the program to resume. From the program's perspective, this was invisible. The instruction that triggered the page fault would simply take longer to complete than usual. The program didn't crash, didn't receive an error, didn't even know that anything unusual had occurred. It just waited, silently, while the machine resolved the page fault, and then continued as if nothing had happened. This invisibility seemed like a feature, and in many ways it was. Programs didn't need special code to handle paging. Programmers didn't need to manage these details explicitly. The abstraction worked. But it also meant that performance became unpredictable in new and subtle ways. A program might run quickly one day, slowly the next, with no changes to the code, no differences in the data being processed. The difference might be that on the slow day, Some other program running concurrently had claimed more physical memory, forcing more aggressive paging. Or the slow day might follow a system restart that had cleared all pages from memory, meaning everything needed to be loaded from disk. Or perhaps the slow day's workload accessed data in a slightly different pattern, one that happened to trigger more page faults. These performance issues could emerge suddenly, seemingly out of nowhere. A program that had run reliably for months might start exhibiting strange delays. Users would complain that terminal response times had degraded. Operations staff would notice that batch jobs were taking longer to complete. But when programmers examined the code, they found nothing wrong. The logic was correct. The algorithms hadn't changed. The data volumes were similar to previous runs. The problem was invisible because it existed in a layer below the program's awareness. The issue was how the program's virtual memory mapped to physical RAM during execution, how its pages were distributed across physical page frames, how frequently it experienced page faults, how much disk I/O was being generated by the paging system. These factors could vary dramatically based on what other programs were running concurrently, how much physical memory was available, how the operating system's paging algorithms happened to behave with this particular workload at this particular moment. Computer scientists developed a concept called the working set to describe this phenomenon. A program's working set was the collection of memory pages it needed to have resident in physical RAM to run efficiently. If the working set fit comfortably in available memory, the program would experience few page faults and would run smoothly. But if physical memory was insufficient to hold the working set, the program would page fault frequently, thrashing between disk and RAM, spending more time waiting for pages to be loaded than actually executing instructions. The insidious thing about working sets was that they could change based on factors that had nothing to do with the program itself. The same program, processing the same kind of data, might have different working set characteristics, depending on what phase of processing it was in, or what other programs were competing for memory, or even just random variations in the order that different execution paths were taken. This produced slowdowns that felt random and untraceable. A program might run quickly through the first part of its processing, then suddenly slow down during a later phase, not because that phase was inherently more complex, but because its memory access patterns happened to interact poorly with the current state of physical memory. The next time the program ran, under slightly different conditions, that slow phase might be fast and a different section might slow down instead. Programmers accustomed to the concrete, deterministic behavior of earlier systems found this maddening. They couldn't easily see how memory was being mapped during execution. There were no simple tools to visualize which pages were resident, which were being faulted, what the paging rate was, or how the working set was evolving over time. The mapping between virtual addresses and physical locations was handled entirely by hardware and operating system software, deep in privileged code that application programmers couldn't access or instrument. This opacity introduced what some programmers began to call ghost bugs, problems that appeared and disappeared without clear cause, performance issues that couldn't be reliably reproduced, behaviors that violated the expected deterministic nature of computer programs. These weren't bugs in the traditional sense. The programs were executing correctly, producing the right results, but they were executing unpredictably with performance characteristics that seemed to have minds of their own. Consider a typical scenario. A batch program runs every night, processing the day's transactions. For weeks, it completes in 2 hours. Then one night, it takes 4 hours. The next night, back to 2 hours. The night after, 3 hours. No code has changed. The transaction volumes are similar. What's happening? Perhaps on the slow nights, a different batch job runs concurrently, one that claims enough memory to force more aggressive paging. Or perhaps the database management system's buffer pools expand under certain workloads, leaving less memory available for application programs. Or maybe the slow nights follow days when certain online transactions left particular data cached in memory, affecting which pages need to be loaded from disk during batch processing. The actual cause might be knowable, in theory, but discovering it would require detailed analysis of memory utilization patterns across all concurrent workloads, understanding of the operating system's paging algorithms, access to system-level monitoring data that might or might not be collected. In practice, these issues often went unexplained, becoming part of that institutional folklore we mentioned earlier. Night processing is slower on Wednesdays. Why? Nobody knows for certain, but it's been true for months, so we plan for it. Minor workload shifts could produce dramatic performance alterations. Adding one more concurrent user, starting one more background job, scheduling one more batch process during an already busy window. Any of these small changes could tip the system from a state where working sets fit comfortably in physical memory to a state where constant paging degraded everyone's performance. The relationship between workload and performance wasn't linear or predictable. There were cliffs, sudden drop-offs, where adding just a bit more load caused disproportionate slowdowns. This made capacity planning difficult and somewhat mystical. How much work could the system handle? It depended not just on total processing requirements, but on the specific mix of programs, their memory access patterns, how their working sets overlapped or competed. Two different sets of programs with similar total CPU requirements might have vastly different memory behaviors, one running smoothly while the other thrashed helplessly. When serious memory-related issues occurred, when performance degraded to the point that it couldn't be ignored or worked around, diagnosis often required post-mortem analysis. The system would be allowed to finish its troubled processing, or perhaps terminated if things became completely unworkable. Then systems programmers would examine dumps, snapshots of memory and system state captured during or after the problem occurred. These dumps were vast, often spanning thousands of pages of hexadecimal numbers representing memory contents, register values, control block states. Buried somewhere in this mass of data might be clues about what had happened, evidence of excessive paging, indications that particular programs' working sets had conflicted, signs that memory was being used in unexpected ways. Finding these clues required deep expertise, pattern recognition developed over years of experience, and often a fair amount of intuition and luck. The machine's internal decisions were becoming increasingly opaque, not just to ordinary users, but even to expert programmers and system administrators. The hardware and operating system were making moment-by-moment choices about memory management, choices that fundamentally affected program behavior and performance. But these decisions happened in silicon and privileged software, visible only indirectly through their effects. This represented a philosophical shift in the relationship between programmers and machines. Earlier computers had been complicated, but ultimately comprehensible. With enough effort, enough study, a determined programmer could understand exactly what the machine was doing and why. But with virtual memory, with hardware-managed paging, with operating system algorithms making dynamic resource allocation decisions, that complete understanding became practically impossible. The systems were doing too much, too quickly, in too many layers of abstraction. The machine was thinking, in a sense, making decisions based on heuristics and policies that might be documented somewhere, but that played out in such complex interactions that predicting or explaining specific behaviors became extremely difficult. And this was just the beginning. Virtual memory was merely one example of a broader trend, a movement towards systems that handled more complexity automatically, but at the cost of visibility and direct control. The ghost bugs it introduced, the mysterious performance variations, the need for post-mortem analysis of inscrutable dumps. These would become familiar patterns as computing systems grew more sophisticated and less transparent. The silent code was becoming not just silent but actively hidden, making decisions in layers that programmers couldn't easily observe, creating behaviors that emerged from complex interactions rather than simple cause and effect. The mystery was deepening, even as the power and capability of these machines continued to grow. At the heart of mainframe batch processing lay a language that perfectly embodied the era's philosophy of computing, a language designed not for human convenience, but for the machine's comprehension, a language that prioritized precision over clarity, compactness over readability. This was job control language, universally known by its initials, JCL, and it was perhaps the most infamous aspect of mainframe computing in the 1970s. JCL was what you wrote when you needed to tell the mainframe what to do. Not the application logic itself, that might be written in COBOL or PL/I or assembler, but the instructions about how to run that application, what resources it needed, what files it should use, what to do if errors occurred, how to chain multiple programs together into a complete workflow. JCL was the scaffolding around the actual work, the metadata that made batch processing possible. But the language itself was cryptic in ways that seemed almost deliberately obscure. Statements were positional, with specific information required in specific columns. Parameters were abbreviated to the point of incomprehensibility. A single JCL statement might specify a dataset name, its storage allocation, its record format, its block size, its disposition before and after the job, and various other technical details, all compressed into a single line dense with slashes, parentheses, equal signs, and abbreviated keywords that followed no intuitive pattern. Consider that this was a language where a simple mistake, a misplaced comma, a missing parameter, an incorrect assumption about dataset characteristics, could cause a job to fail. And unlike modern programming environments where you might test your code interactively, making small changes and immediately seeing results, JCL was typically written at a desk, on paper, or using a text editor, then submitted to the system to be executed hours later, with success or failure discovered only when printed output was delivered the next morning. This delay between writing and execution created a peculiar development cycle. A programmer might write JCL for a new batch job, carefully checking the syntax, reviewing the parameter specifications, verifying the dataset names. The job would be submitted, entering a queue of work waiting for execution. Hours would pass. Eventually, the job would run, or attempt to run. The next day, the programmer would receive the printed output, only to discover a JCL error on the third statement, a typo that had escaped notice during review. The job had failed immediately, but the programmer was only learning about it now, 18 hours after submission. The correction would be made, the job resubmitted, another cycle of waiting would begin. In environments where testing windows were limited, where production batch schedules were tightly packed, it might take days or even weeks to debug complex JCL, with each iteration requiring another overnight cycle, another day of waiting to discover if this attempt succeeded or revealed yet another subtle error. The cryptic nature of JCL wasn't accidental. The language had been designed in an era when computer time was precious and human time was comparatively cheap. The goal was to allow precise specification of job requirements in a format that the operating system could parse efficiently. Readability for programmers was a secondary concern at best. The assumption seemed to be that professionals would learn the language, would become fluent in its peculiar syntax, would adapt to its requirements. And they did adapt, developing a kind of literacy in JCL that became a valuable skill, even a mark of expertise. Senior programmers could read JCL statements that looked like gibberish to newcomers and immediately understand what resources were being requested, what the job flow would be, where potential problems might lurk. But this expertise took years to develop, and even experienced practitioners could make mistakes, could overlook subtle errors that would only manifest under specific circumstances. In the early DOS/360 and DOS/VS environments, JCL often included specifications that seemed unnecessarily detailed, even pedantic. Jobs might need to specify not just that they required a tape drive, but exactly which model of tape drive, which specific hardware configuration. This level of detail reflected the operating system's limited ability to abstract hardware resources, to make intelligent decisions about resource allocation on behalf of the programmer. If your job specified that it needed a 2400 series tape drive, the system would assign a 2400 series tape drive. If none were available, the job would wait, even if a newer, fully compatible 3400 series drive sat idle. The system did what it was told, exactly what it was told, with no flexibility to interpret intent or make reasonable substitutions. This rigidity had consequences that extended far beyond simple inefficiency. When organizations upgraded their hardware, replacing older devices with newer models, production jobs that had run successfully for years could suddenly start failing. The JCL still specified the old hardware model numbers, and the system, literal-minded as always, couldn't find devices matching those specifications because they'd been physically removed and replaced. These failures were silent in a particular way. The job didn't crash with an obvious error. It simply waited, queued, looking for a resource that no longer existed. Eventually, someone would notice that the job hadn't completed, would investigate, would discover the mismatch between requested and available hardware, would update the JCL. But in the meantime, the job that calculated payroll or updated inventory or generated critical reports had simply not run, its absence perhaps unnoticed until someone asked where the expected output was. Simple hardware upgrades could silently break long-standing production jobs, introducing failures that had nothing to do with the application logic, nothing to do with the data being processed, everything to do with these detailed hardware specifications embedded in JCL that might have been written years earlier by someone who'd long since moved to another position or another company. The batch processing model itself introduced a fundamental disconnect between action and result. When you submitted a job, you were essentially writing a message to the future, a set of instructions that would be carried out later, when resources became available, when the job's priority brought it to the front of the queue, when the necessary datasets were available and the required hardware was free. There was no interactive feedback during this process. You couldn't watch the job run, couldn't see it progress from one step to the next, couldn't intervene if something started going wrong. The job was submitted, it disappeared into the system, and eventually, hours later, the next morning, sometimes days later if the job was low priority or if problems intervened, results would appear. Those results came in the form of printed output, thick stacks of paper that would be delivered to programmers' desks or to designated pickup locations. The paper would contain the job log, showing which steps had executed, what return codes they'd produced, what messages the system had generated. Then would come the application output itself, reports, data listings, error messages, whatever the program had been designed to produce. Only by reading through this printed output could you discover whether the job had succeeded or failed. A JCL error might be obvious, reported in the first few lines of the log, but subtler problems, incorrect data, logic errors, unexpected conditions in the application code, might be buried deep in hundreds or thousands of pages of output, requiring careful review to detect. This created a strange temporal relationship with the computing process. You wrote JCL and submitted a job in the afternoon. The actual execution happened overnight, while you were home, while the machine ran through its batch queue in the silent hours. You discovered the results the next morning, examining printed output from a process that had occurred hours ago, reviewing messages generated by programs running in your absence. Debugging became an exercise in archaeological reconstruction. The printed output was evidence, traces left by a process that was now complete, finished, gone. You would study these traces, trying to understand what had happened, what had gone wrong, what needed to be changed. Then you would modify the JCL, or the program code, submit another job, and wait through another cycle. Over time, batch processing became organized into chains of interdependent jobs. The nightly processing for a typical business might involve dozens, or even hundreds of separate batch jobs, each performing a specific function, each depending on the successful completion of earlier jobs in the sequence. The first job might extract transaction data from online systems, creating files that subsequent jobs would process. The second job might sort that data. The third might update master files. The fourth might generate summary records. The fifth might produce reports. Each step depended on the previous step having completed successfully, having produced its output files in the expected format, having left the system in a state ready for the next stage of processing. These chains became long and deeply interdependent, representing workflows that had evolved over years, accumulating complexity as new requirements emerged and new steps were added. The chain that had started as 5 jobs might grow to 50, each one a critical link, each one a potential point of failure. And here's where things became truly mysterious. A single mis-sequenced job step, a single error in one program deep in the middle of the chain, could cause anomalies that wouldn't be detected until days later. Perhaps a job that was supposed to run third accidentally ran fourth instead. It completed successfully, generated its output, appeared to work correctly. But because it ran out of sequence, it used data that hadn't been fully prepared yet, or it updated a file before another process had finished reading it. The immediate effects might be subtle or invisible. The job produced output that looked reasonable. The next jobs in the chain ran successfully. The nightly processing completed. But the data was wrong in small ways, corrupted in subtle fashions that wouldn't become apparent until later, when someone tried to reconcile accounts, or when a report showed impossible values, or when a downstream process failed because it encountered data that violated expected constraints. By the time the problem was discovered, the causal connection to its source had been obscured by time and intervening processes. The error that occurred on Monday night might not be detected until Thursday morning. Investigating would require reconstructing the entire sequence of batch processing across multiple nights, examining logs and output from dozens of jobs, trying to trace backward through the chain of dependencies to find where things had first gone wrong. Cause and effect felt disconnected in time, separated by hours or days, mediated by complex sequences of processing that made simple linear reasoning inadequate. The batch processing environment created feedback loops that were measured in days rather than seconds, where the consequences of actions might not become apparent until long after those actions had completed, where the system state at the moment of execution was different from the system state when problems were discovered. This temporal disconnect extended to how people thought about the systems. The machine ran overnight, processing its queues of work in the darkness, in the silence of the computer room, where only a few operators monitored the console, where jobs executed in sequence or in parallel according to priorities and dependencies that were themselves encoded in JCL and scheduling parameters. The execution often seemed to unfold beyond human supervision, an autonomous process where the machine followed its instructions faithfully, but without understanding, where the complex interplay of concurrent jobs and shared resources and temporal dependencies created emergent behaviors that no individual programmer had designed or anticipated. Operators could monitor the overall progress, could see that jobs were running, could intervene if systems crashed or if jobs appeared to be stuck. But they typically didn't understand the application logic, didn't know what the jobs were supposed to accomplish, couldn't judge whether the results were correct. They knew if a job completed with a return code indicating success or failure, But that surface indication might not reflect deeper problems in the data being processed or the results being produced. Systems programmers understood the operating system and its behavior, but might not know the details of business applications. Application programmers understood their programs, but might not fully grasp the operating system's resource management or the interactions between concurrent jobs. Business analysts understood the requirements, but might not know how they'd been implemented in code. Everyone had partial knowledge, a piece of the puzzle, but complete understanding of the entire system. Hardware, operating system, scheduling, JCL, application logic, data flows, dependencies, exceeded what any individual could hold in their mind. And so the batch processing ran, night after night, following JCL scripts that might have been written years ago, executing programs whose original authors might have retired, processing data through chains of transformations that had accumulated organically over time. It mostly worked, this intricate clockwork of scheduled jobs and interdependencies. But when it failed, when something went subtly wrong, understanding what had happened and why often felt less like engineering and more like detective work, piecing together clues from printed logs, trying to reconstruct events that had occurred in your absence, in the machine's silent nocturnal operations. The mystery deepened with every added complexity, every new job added to the chain, every additional dependency introduced into the system. The code was silent, yes, but it was also temporal, distributed across time in ways that made causality slippery and understanding elusive. In the world of mainframe computing during the 1970s, software existed at a scale that challenged human comprehension in fundamental ways. Large COBOL programs, the workhorses of business data processing, routinely exceeded 100,000 lines of code. To put this in perspective, imagine a printed listing of such a program. It would fill multiple thick binders, thousands of pages of code that might take weeks just to read through sequentially, let alone understand. These weren't compact, elegant algorithms compressed into minimal code. COBOL was verbose by design, using English-like syntax that made individual statements readable, but contributed to the overall bulk. A simple calculation that might take one line in a mathematical notation could easily expand to 5 or 10 lines of COBOL, with explicit variable declarations, section headers, paragraph names, and detailed procedural specifications. But size alone doesn't fully capture the complexity. These massive programs weren't standalone entities. They were parts of larger systems, components in intricate workflows where multiple programs worked together, passing data back and forth, each one handling a piece of the overall business process. The primary mechanism for this coordination was shared datasets. One program would write its output to a file, a dataset residing on disk storage. Another program would read that same dataset as its input, processing the data, perhaps transforming it, then writing its own output to yet another dataset. A third program might read from multiple datasets, combining their data, performing cross-referencing or validation, producing summary files or reports. This chaining through shared datasets created webs of dependencies that could be extraordinarily complex. A single business process, month-end closing for instance, might involve dozens of programs executing in a carefully orchestrated sequence, each one depending on files created by previous programs, each one producing files that subsequent programs required. The state of the system at any point wasn't contained within a single program's memory or even within a single dataset. It was distributed across dozens of files, hundreds of programs, thousands of parameters and flags and control records. Global state, in the sense of information that affected the behavior of multiple programs, was everywhere and nowhere, scattered through the file system in ways that could be difficult to track or understand. Within individual programs, the situation was often no clearer. COBOL and other languages of the era made extensive use of goto statements, direct jumps from one point in the code to another. The goto was a simple, powerful control structure. When execution reached a goto statement, it would immediately jump to a named label elsewhere in the program, continuing execution from that new location. This was flexible, certainly. You could implement any control flow logic imaginable using gotos. But flexibility came at the cost of clarity. When reading through code, you couldn't simply follow the statements sequentially to understand what the program did. At any moment, a goto might redirect execution to somewhere entirely different, somewhere that might be hundreds or thousands of lines away, in a completely different section of the program. Programs developed complex, tangled control flows where execution bounced from section to section, where the same code might be reached from multiple different gotos, where understanding what happened after a particular piece of logic required searching through the entire program to find all possible goto targets. Flowcharting such programs became exercises in drawing spaghetti diagrams, masses of interconnected boxes and arrows that looked more like abstract art than logical structures. Computer scientists were beginning to argue for structured programming, for control flow based on loops and conditionals and subroutines, rather than arbitrary jumps. But in the 1970s, particularly in COBOL environments, the goto was still king, and legacy programs that might have been written in the 1960s and were still running in the 70s, were full of them. This made reasoning about program behavior extraordinarily difficult. To understand what would happen in a particular scenario, you couldn't just read through the relevant section of code. You had to trace possible execution paths, following gotos, tracking which flags and variables might be set when you reached particular decision points, accounting for all the possible ways that execution might arrive at a given statement. The potential for subtle errors was immense. A single incorrect flag, a single variable set to the wrong value, a single record in a file with corrupted or unexpected data. Any of these could ripple through entire batch runs, affecting not just one program, but cascading through the chain of dependent programs that processed the contaminated data. Consider a scenario. During overnight processing, an early job in the chain encounters a data record that's malformed in some subtle way. The program's error checking doesn't catch this particular form of corruption. Perhaps it's checking for missing data, but not for data that's present but invalid. Or perhaps the check is there, but contains a bug that allows the bad record through. The program processes this record incorrectly, producing a result that's wrong, but not obviously impossible. This incorrect result gets written to an output file. The next program in the chain reads that file, including the incorrect record. Its processing logic makes certain assumptions about the data, assumptions that are usually valid, but that happen to be violated by this particular incorrect record. The program doesn't crash, but it calculates something wrongly, perhaps applying the wrong business rule, or looking up data from the wrong reference table. Its output is further corrupted, now in ways that compound the original error. This continues through the chain. Each program adds a little more distortion, moves a little further from correct results. By the end of the nightly processing, reports are generated with subtly wrong numbers. Balances don't quite match. Totals are off by amounts that aren't immediately obvious. Someone reviewing the reports might notice something seems wrong, or they might not. The errors might fall within ranges that look plausible, that don't trigger immediate red flags. Days or weeks later, during month-end reconciliation or during an audit, the discrepancies become undeniable. Now begins the process of tracking backward, trying to find where things first went wrong. Logs from days ago must be retrieved. Saved copies of intermediate datasets must be examined. Programs must be analyzed to find where they might have mishandled data. The single incorrect flag or record that started the cascade must be identified, its source understood, corrections implemented. The complexity was compounded by multi-programming. the operating system's ability to run multiple jobs concurrently. This was essential for efficient use of expensive mainframe hardware. While one program waited for disk I/O to complete, the processor could be executing instructions from another program. Multiple batch jobs could run simultaneously, sharing the CPU, the memory, the I/O channels. But concurrency introduced a new class of problems. Programs that worked correctly in isolation might interfere with each other when run concurrently. Two programs might try to update the same file simultaneously, leading to corrupted data if proper locking mechanisms weren't in place. One program's heavy use of disk I/O might slow another program's processing. Memory contention could trigger paging storms that degraded everyone's performance. Most insidiously, timing-related issues could appear. A program might work correctly 99 times out of 100, but occasionally, when the timing of its execution happened to align with another program's operations in just the wrong way, something would go wrong. A file might be accessed before another program had finished writing it. A shared resource might be locked just when another program needed it. A race condition, where the correctness of results depended on the precise timing of operations, might produce incorrect output. These timing-related issues were intermittent, appearing unpredictably, often impossible to reproduce on demand. A job might fail overnight, but when rerun the next morning for debugging purposes, it would work perfectly. The conditions that triggered the problem, the specific combination of concurrent workload, timing, and system state, might not recur for days or weeks. This led to a peculiar operational practice. When jobs failed, operators would often simply rerun them, hoping the issue would disappear. And often it did. The second run, occurring at a slightly different time with a slightly different mix of concurrent activity, might complete successfully where the first run had failed. The job would be marked as successful, processing would continue, and the underlying issue, whatever timing-dependent problem had caused the initial failure, would remain uninvestigated and unresolved, waiting to manifest again under the right circumstances. Over time, programs grew organically, evolved rather than being designed. New features were added, new business requirements implemented. But rarely was there time or budget for refactoring, for restructuring the code to accommodate new functionality cleanly. Instead, new code was grafted onto old, new sections were added at the end, new go-tos were inserted to jump to the new logic. A program that started as 10,000 lines might grow to 50,000, then to 100,000, through this process of accretion. Each addition made sense in isolation. A new requirement needed to be implemented, and the programmer found a way to add it to the existing code. But collectively, these additions transformed the program into something that no individual fully understood, a structure that had grown beyond the ability of human minds to fully comprehend. Understanding the full execution paths through such programs became nearly impossible. There were simply too many possible paths, too many conditional branches, too many go-tos, too many ways that execution could flow through the code. Testing couldn't cover all possibilities. Code review couldn't trace all paths. The programs worked, mostly, through a combination of careful initial design, conservative changes, extensive testing of normal scenarios, and a certain amount of luck that edge cases didn't occur too frequently. Documentation struggled to keep pace with this evolution. When a program was first written, documentation might be created. Descriptions of what the program did, specifications of its inputs and outputs, flowcharts showing its major logic flows. But as the program evolved, as changes were made year after year, the documentation rarely received the same attention. Updating documentation was time-consuming and didn't directly contribute to implementing new features or fixing urgent bugs. In environments where programmers were always under pressure to deliver the next enhancement or resolve the next crisis, documentation updates were perpetually deferred. The written descriptions became outdated. Flowcharts no longer matched actual code structure. Specifications documented behavior that had been changed or removed. Systems evolved faster than documentation, opening a widening gap between what was written down and what actually existed in production. Newcomers to the team would find that they couldn't rely on documentation to understand the systems. Instead, they had to read the code itself, trace through the actual logic, perhaps talk to senior programmers who'd been maintaining these systems for years and who carried understanding in their heads that had never been written down. This created knowledge silos and dependencies on key individuals. Certain programmers became indispensable because only they truly understood particular critical systems. They'd maintained those systems for years, had made most of the changes, knew where all the quirks and workarounds were hidden. Losing such a person, to retirement, to a new job, to illness, could be catastrophic, leaving systems that were too complex to understand quickly, that would take months or years for someone new to learn adequately. And so organizations found themselves running on software that was powerful, that handled critical business operations, that processed millions of transactions and billions of dollars, but that had grown beyond the point where any individual, or even any team, could claim complete understanding. The systems worked through the accumulated efforts of many programmers over many years, each contributing pieces that fit together into functioning wholes, but where the full picture, the complete understanding of every interaction and dependency and edge case, exceeded human cognitive capacity. This was programming at massive scale in the 1970s. Code measured not in thousands, but in hundreds of thousands of lines. Systems that spanned not single programs, but dozens or hundreds of interconnected components. Control flows that wound through intricate networks of go-tos and conditional branches. Execution that happened concurrently across multiple jobs with subtle timing dependencies. Growth that was organic and incremental, and ultimately produced structures too complex for comprehensive understanding. The mystery wasn't just in how the machines worked, but in how the software worked, how these vast accretions of code managed to function, how businesses operated reliably on foundations that no one person could fully explain. The silent code executed, night after night, processing the work of commerce and government and industry, and mostly it worked through careful construction and cautious modification, and a certain necessary faith that the systems would continue to do what they'd always done, even as they grew beyond complete human comprehension. In the high-throughput environments of 1970s mainframe computing, where millions of transactions flowed through systems daily, where vast databases grew steadily larger, where magnetic tapes and disk packs held the essential records of commerce and government, a particularly insidious class of problems began to emerge. These were issues that didn't announce themselves with crashes or error messages, that didn't halt processing or trigger alarms. They were silent, invisible, and deeply troubling once discovered. They were cases of silent data corruption. Data corruption itself wasn't new. Computer systems had always been vulnerable to errors, hardware malfunctions, software bugs, operator mistakes. But most errors were loud. A program would crash, producing an error code and a memory dump. A disk drive would fail, making its data inaccessible. An operator would mount the wrong tape, and the mismatch would be detected immediately when the program tried to read unexpected data. Silent data corruption was different. This was data that changed without warning, that became incorrect while the system reported everything was functioning normally. A value stored to disk might not be the same value read back later. A record written to tape might have different contents when retrieved months later. Individual bits, the fundamental zeros and ones that represented all information in digital form, might flip from one state to another, corrupting the data they encoded. The physical media of the error were mechanical, magnetic, inherently imperfect. Disk drives spun platters coated with magnetic material at high speeds. with read/write heads floating impossibly close to the surface, separated by distances measured in millionths of an inch. Any tiny imperfection, a microscopic dust particle, a slight vibration, a momentary fluctuation in the drive electronics, could cause a miswrite, where data was written incorrectly, or a misread, where data was read back differently than it had been stored. Magnetic tapes, those reels of brown plastic wound with magnetic coating that served as the primary backup and archival medium, were even more vulnerable. They could be stretched by mechanical stress. Their magnetic properties could degrade over time. Temperature and humidity variations could affect reliability. Physical damage, scratches, creases, contamination, could render portions of a tape unreadable or cause data to be read incorrectly. The industry had developed checksums and error detection codes to combat these problems. When data was written, additional information would be calculated and stored alongside it. Values derived from the data itself that could be recalculated when the data was read and compared to verify that nothing had changed. If the recalculated checksum didn't match the stored checksum, an error had occurred and the system would report it. But checksums weren't perfect. They could detect many errors, but not all errors. Certain specific patterns of corruption, particular combinations of bit flips, could produce corrupted data that nevertheless had a valid checksum, appearing correct when it wasn't. And sometimes the checksum itself would be corrupted along with the data it was supposed to protect, making detection impossible. More fundamentally, checksums were only calculated at certain points. Data might be verified when written to disk, and again when read back, but not continuously while it sat on the disk. If a bit flipped on the disk surface between the write and the read, perhaps due to magnetic decay or cosmic radiation, or some subtle hardware problem, that corruption might not be detected until much later, if ever. When such corruption occurred, the affected data would simply be wrong. A customer's account balance, stored as a binary number, might have a bit flip that changed it from one value to another. The change might be small, a single bit in a multi-byte number, or it might be large, depending on which bit was affected. The least significant bit flipping might change a value by 1. The most significant bit flipping might change it by millions. And here's where the silent nature of the problem became truly problematic. That corrupted value would be treated as correct by all subsequent processing. Programs reading the account balance would get the wrong value and wouldn't know it was wrong. Calculations would be performed using the corrupted data. Reports would be generated showing incorrect information. And if that data was backed up before the corruption was discovered, the backup would faithfully preserve the incorrect value. Backup procedures, designed to protect against data loss, could actually propagate corruption. Every night, or every week, systems would be backed up to tape. If corruption had occurred since the last backup, the corrupted data would be written to the new backup tape, replacing the previously correct version. If this continued for months, every generation of backups would contain the corrupted data, making it impossible to restore to a correct state without going back to very old tapes that might themselves be degraded or no longer available. The first sign of trouble might come much later, disconnected in time from the original corruption event. Perhaps during a quarterly audit, accountants would notice that totals didn't match, that there were discrepancies that couldn't be explained by legitimate transactions. Or a customer would complain that their balance was wrong, triggering an investigation. Or a year-end reconciliation would reveal mysterious differences between different systems' views of the same data. By the time the problem was discovered, tracing back to the original cause could be nearly impossible. When did the corruption occur? Which system was affected first? How had the corrupted data propagated through the various programs and databases? What other data might have been affected? These questions often had no clear answers, buried as they were under months of subsequent processing, layers of backups, cascades of calculations that had used the corrupted values. Errors propagated quietly through trusted systems, hidden in the normal flow of data, indistinguishable from correct values unless someone had reason to verify them specifically. And verification was challenging. For an account balance or inventory quantity, you might be able to go back to source documents, add up individual transactions, recalculate what the correct value should be. But for derived values, for summary totals, for the results of complex calculations, verification might require rerunning months of processing, a task that could be logistically impossible. Beyond hardware-level corruption, there were also numerical precision issues that produced their own forms of silent data corruption. Mainframe systems used various numeric representations: floating point for scientific calculations, packed decimal for business data. Each had its own quirks, its own peculiarities that could introduce subtle errors. Floating point arithmetic, used for calculations involving very large or very small numbers, or numbers with fractional parts, was inherently imprecise. Numbers were represented with a limited number of significant digits, and calculations could introduce rounding errors. Most of the time, these errors were tiny, far smaller than anyone cared about. But they were there, small discrepancies between the mathematically exact result and the computer's approximation. Packed decimal, commonly used in COBOL programs for financial calculations, stored numbers in a format where each byte could hold 2 decimal digits. This was more precise for decimal arithmetic than floating point, but it had its own issues. Division operations could produce results that needed to be rounded to fit the available precision. Numbers with many decimal places might lose trailing digits. In a single calculation, these tiny discrepancies meant nothing. But business data processing involved performing calculations on millions of records, accumulating totals, calculating averages, applying formulas repeatedly. And here's where small rounding errors could compound over time. Imagine a calculation performed on 1 million account records, where each calculation introduces a rounding error of 1/10 of a cent individually. These errors are invisible. Financial systems typically tracked amounts to the penny, so 1/10 of a cent was below the threshold of representation. But accumulated across 1 million calculations, those tiny errors could sum to thousands of dollars. Financial systems would appear to quietly lose or create money, with discrepancies that couldn't be traced to any specific transaction or calculation, but that emerged from the accumulation of countless tiny imprecisions. General ledgers wouldn't balance perfectly. Asset totals would be slightly off. The differences were usually small in percentage terms, but could be significant in absolute amounts when dealing with large-scale financial operations. Accountants and auditors would discover these discrepancies and would try to track them down, often assuming they represented actual errors, misrecorded transactions, software bugs, perhaps even fraud. Extensive investigations might be launched. People might spend weeks examining records and code, only to eventually conclude that the discrepancies were artifacts of computational precision limits, unavoidable consequences of performing arithmetic in finite precision on massive datasets. But proving this was difficult. How could you be certain that all discrepancies were due to rounding rather than actual errors? How could you distinguish between the expected accumulation of tiny imprecisions and a real problem? Corrupted data, a programming bug, a fraudulent transaction hidden among millions of legitimate ones. Organizations developed various strategies to cope with these issues. Suspense accounts were created to hold unreconciled differences. Tolerance thresholds were established. Differences below a certain amount were simply accepted as unavoidable artifacts of the system. Periodic adjustments were made to bring totals back into balance, essentially sweeping the accumulated errors into a correction entry that made the books balance, even if it didn't explain the discrepancies. These practices worked, in a pragmatic sense. The systems continued to operate, financial reporting continued, businesses functioned. But there was always uncertainty lurking beneath the surface. When you found a discrepancy, was it an acceptable rounding error or something more serious? When you made an adjustment to balance the books, were you correcting for computational imprecision, or were you obscuring a real problem? Data integrity issues were rarely publicized. No organization wanted to admit that their computer systems might be silently corrupting data, or that their financial totals didn't quite add up, or that they couldn't fully explain all the discrepancies in their records. This was sensitive information, potentially damaging to customer confidence, possibly relevant to regulatory compliance, definitely embarrassing to the technical staff responsible for the systems. So these problems were handled quietly, internally, with minimal documentation that might later be discoverable in audits or legal proceedings. Teams would work to investigate and resolve issues, to implement better checksums, or more frequent verification, or more precise arithmetic. But the broader community often remained unaware, with each organization assuming their problems were unique, possibly due to their specific hardware or software or operational procedures, unaware that similar issues were occurring across the industry. This silence meant that lessons weren't shared, that solutions developed by one organization couldn't benefit others facing similar challenges, that the industry as a whole was slower to address these fundamental reliability problems than might have been possible with more open communication. The temporal disconnection between cause and effect made these problems particularly difficult to address. A bit flip occurring in January might not be detected until April. A rounding error in daily processing might only become apparent during quarterly reconciliation. Corrupted data might propagate through backups for months before anyone noticed something was wrong. By the time you discovered the problem, the original fault might be long gone. The hardware that caused the bit flip might have been replaced. The specific calculation that introduced excessive rounding error might have been run months ago and couldn't be easily recreated. You were left investigating historical events with limited evidence, trying to reconstruct what had happened based on partial information, logs that might not capture the relevant details, backups that preserved effects but not causes. This created a peculiar form of technological archaeology. Systems analysts would examine old backup tapes, comparing data across different points in time, looking for when values changed unexpectedly. Programmers would analyze code, looking for calculations that might accumulate excessive rounding errors. Operations staff would review hardware maintenance logs, looking for equipment problems that might correlate with suspected corruption events. Sometimes these investigations succeeded, identifying specific causes and enabling targeted fixes. But often they ended inconclusively, with suspicions but not certainty, with likely explanations but not definitive proof. The systems would be monitored more carefully going forward. Additional verification checks might be added, but the historical problems remained mysteries, outcomes that had changed long after the original faults occurred, silent alterations to reality recorded in magnetic patterns on spinning disks and wound tapes. The data that organizations trusted, that they based decisions upon, that they reported to regulators and shareholders, that they used to calculate taxes and pay employees and bill customers. This data was less certain, less reliable than most people realized. It was mostly correct, usually accurate enough for practical purposes, but it was subject to silent corruption, to subtle drift, to accumulated imprecisions that could produce real consequences, even if they rarely produced catastrophic failures. And this uncertainty was itself mysterious, hidden, unspoken. The systems projected authority and precision. Computers were supposed to be exact, literal, perfectly reliable in their storage and processing of information. But the reality was messier, more fallible, more human in its imperfection than the clean abstraction of digital computing suggested. The silent code processed data that was itself sometimes silently wrong. and the gap between perception and reality, between assumed reliability and actual behavior, was yet another layer of mystery in these inscrutable machines. The process of debugging software on 1970s mainframes bore little resemblance to the interactive, immediate feedback that would characterize later development environments. Instead, it was an indirect, delayed, almost ritualistic process where programmers worked at one remove from the systems they were trying to fix, where changes took effect overnight, where evidence of problems came in the form of cryptic printed output delivered hours after the failure occurred. Many installations, particularly those running critical business systems, maintained strict policies about production code. The libraries where production programs resided, the actual executable code that processed real transactions, updated live databases, generated official reports, were protected, secured, locked down. Programmers didn't have direct write access to these libraries. They couldn't simply edit a production program, make a change, and immediately run the modified version. This restriction made sense from a control and stability perspective. Production systems needed to be reliable, predictable, protected from casual modifications that might introduce errors. Changes needed to be reviewed, tested, approved through formal procedures. But the restriction also meant that the process of fixing bugs in production code became elaborate and time-consuming. When a programmer needed to modify a production program, they would work on a copy in a development or test library. They would make their changes, test them as thoroughly as possible in the non-production environment, then submit a formal change request. This request would document what was being changed and why, would include the modified source code, would go through approval processes. Eventually, if approved, the change would be applied to production. But this application wasn't instantaneous or direct. It happened through batch jobs, scheduled processes that ran overnight or during designated maintenance windows. A systems programmer or change control administrator would submit a job that would compile the modified source code, link it into an executable program, and replace the old version in the production library with the new version. The programmer who made the change wouldn't personally perform this production update. They would submit the request, it would enter a queue, it would be processed according to schedule and priority. The actual modification of production libraries happened in batch, often overnight, executed by automated procedures or by operations staff following documented processes. This created a strange temporal delay in the development cycle. You might make a change on Tuesday afternoon, submitting it for production implementation. The change might be scheduled for the overnight batch window Tuesday night. Wednesday morning, you would arrive at work to discover that your code had been updated, that the production library now contained your modifications. The code appeared to have changed itself overnight, transformed while you were away, altered by processes you didn't directly control or observe. If the change worked, this was merely bureaucratic overhead, a slow but manageable process. But if the change failed, if it introduced a new bug, or didn't actually fix the problem it was meant to address, you wouldn't discover this until the modified program had run in production, had processed real data, had failed in real operations. And when failures occurred, the diagnosis process was equally indirect and delayed. Production programs that encountered errors would typically terminate, generating what was called a dump, a snapshot of the program's memory and state at the moment of failure. This dump would be written to a dataset, and eventually, it would be printed and delivered to the programmer responsible for the failing program. This delivery might happen hours after the actual failure. A program might fail at 2 a.m. during overnight batch processing. The dump would be generated, queued to a printer, printed when printer capacity was available, sorted by job name or programmer ID, placed in a designated pickup location. The programmer might not see it until they arrived at work Wednesday morning, 8 or 10 hours after the actual failure occurred. What they received was intimidating. a thick stack of paper covered in numbers and codes that required specialized knowledge to interpret. The first pages might show register contents, the values that had been in the computer's internal registers at the moment of failure. These were hexadecimal numbers, base 16 notation, that packed more information into fewer digits than decimal, but that required translation to understand. Following the registers would be memory dumps, pages and pages of hexadecimal values representing the contents of the program's memory space. Code and data mixed together, distinguishable only to someone who understood the program's structure, who could recognize patterns that indicated executable instructions versus numeric data versus text strings. Scattered through the dump would be terse codes, completion codes, reason codes, messages that indicated what type of failure had occurred. A 0C7 might indicate invalid data in a numeric field. A 0C4 might suggest a protection exception, an attempt to access memory the program wasn't authorized to use. A 322 might indicate a timeout, a program that had run too long and been terminated by the operating system. These codes were standardized, documented in thick reference manuals that programmers kept on their desks. But the codes themselves were just starting points. They told you the symptom, but not the cause. They indicated what had gone wrong at the moment of failure, but not why it had gone wrong. What sequence of events had led to that failure state. To understand that, programmers had to manually trace execution paths from the paper dumps. They would identify where in the program the failure occurred, which instruction had been executing when the error happened. They would examine the memory contents around that location, trying to understand what data the program had been processing. They would work backward, reconstructing the sequence of operations that had led to that point. This was painstaking work, requiring deep knowledge of the programming language, the operating system, the hardware architecture. You had to understand how different data types were represented in memory, how addresses were calculated, how the program's control flow worked. You had to be able to read hexadecimal fluently, to recognize patterns, to make inferences from limited information. Often, the dump alone wasn't sufficient. You needed to understand the program's logic, its data structures, its assumptions about input data. You might need to examine the input files that the program had been processing, looking for data that might have triggered the failure. You might need to review recent changes to the program or to related systems, looking for modifications that could have introduced new failure modes. The debugging process became detective work conducted with fragmentary evidence, trying to reconstruct events that had occurred hours ago in your absence, piecing together clues from printed snapshots of machine state. And all of this happened without the ability to interactively explore the failure, to rerun the program with breakpoints, to inspect variables during execution, to test hypotheses immediately. The natural instinct when debugging is to add diagnostic output, to insert print statements or logging calls that would show what the program was doing, what values variables held at critical points, which execution paths were being taken. But in the mainframe batch environment, this instinct was constrained by practical considerations. Extra logging meant extra output, which meant more data written to files, which meant more disk I/O, which meant slower execution. It meant larger output files that consumed disk space, that took longer to print, that someone would have to review. Most significantly, it meant higher CPU consumption, and CPU time was expensive. It was literally metered and billed, with each job charged based on how much processor time it consumed. Organizations were cost-conscious about CPU usage. Programmers were expected to write efficient code, to minimize unnecessary processing. Adding extensive diagnostic logging to a production program that processed millions of records could significantly increase its runtime and cost. Management was unlikely to approve such overhead, especially if it persisted beyond the immediate debugging effort. So logging was minimized, used sparingly, added only when absolutely necessary, and removed as soon as the problem was diagnosed. Programs ran with minimal instrumentation, producing only essential output, leaving their internal operations largely invisible. This created situations where bugs would sometimes disappear when diagnostic prints were added. A program would fail reliably, consistently, under production conditions. The programmer would add logging to understand what was happening, would recompile and retest. And suddenly, the bug wouldn't reproduce. The program would run successfully, processing the same data that had previously caused failures, but now completing without error. Remove the diagnostic logging, and the bug would return. Add it back, and the program would work again. The very act of trying to observe the problem would change the program's behavior, making the problem disappear. This phenomenon had rational explanations. Adding diagnostic code changed the program's timing. It took longer to execute, giving time-dependent issues different behavior. It changed memory layout. The extra code and its data structures shifted where other variables resided in memory, potentially avoiding memory-related problems that depended on specific address alignments or memory patterns. It changed optimization. Compilers might generate different code when the program structure changed, potentially avoiding bugs that were artifacts of specific compiler optimizations. But understanding these rational explanations didn't make the debugging process any less frustrating. You had a problem that occurred reliably in production, but that you couldn't observe without making it disappear. The bug existed in a quantum state of sorts, present when unobserved, absent when you tried to look at it. This fostered stories of code that knew it was being watched, semi-serious folklore that attributed awareness to programs, suggesting they behaved differently under observation. Programmers would joke about Heisenberg bugs, named after the quantum physics principle where observation affects the observed system. They would develop superstitious-seeming practices, testing code at the same time of day it failed in production, avoiding certain types of diagnostic output, maintaining subtle aspects of the execution environment that seemed to matter even if no one understood why. Some bugs could only be diagnosed through inference and deduction. You couldn't see them directly, but you could see their effects. You could examine the data corruption they left behind, the incorrect results they produced, the system state they created. From these effects, you could reason backward to possible causes, developing hypotheses about what might have happened. Then you would make a change based on that hypothesis, perhaps adding a check for a data condition you suspected was causing problems, or reordering operations to avoid a race condition, or changing how memory was allocated to prevent a suspected overflow. You would submit this change, wait for it to be applied to production, wait for the next occurrence of the problem to see if your fix worked. If the problem stopped occurring, your hypothesis was probably correct, though you could never be completely certain. Maybe the problem had been intermittent and would have stopped anyway, or maybe your change had just made it less frequent rather than eliminating it. If the problem continued, your hypothesis was wrong, and you needed to develop a new theory, make a different change, wait again. This iterative process could take weeks or months for particularly difficult bugs. Each iteration required a production deployment, a waiting period to see if the problem recurred, analysis of whether the change had helped. The feedback cycles were measured in days or weeks rather than minutes or hours. Debugging became ritualistic and indirect, a process that involved more thinking and less direct observation than debugging in more immediate environments. You couldn't just run the program and watch what it did. You had to imagine what it was doing, construct mental models of its execution, reason from abstract principles and limited evidence. Experienced programmers developed deep skills in this form of debugging. They could read hexadecimal dumps fluently, could reconstruct complex execution scenarios from minimal clues, could form accurate hypotheses about problems based on subtle patterns in failure symptoms. This expertise was hard-won, developed over years of practice, and it became valuable institutional knowledge that was difficult to transfer to newcomers. But it also meant that debugging was slower, more uncertain, more dependent on individual expertise than it needed to be. Problems that might have been quickly identified with interactive debugging tools instead required extensive analysis and multiple iteration cycles. The opacity of the systems, the temporal delays in the development and deployment process, the cost constraints that limited instrumentation, all of these combined to make debugging a dark art practiced by specialists who had learned to see patterns in the shadows. The mystery of the silent code was compounded by this debugging in the dark. This process of fixing problems you couldn't directly observe, of making changes that wouldn't take effect until tomorrow, of reasoning from printed snapshots to understand behavior that had occurred hours ago in circumstances you couldn't recreate. The systems ran, mostly they worked, and when they didn't, understanding why required patience, expertise, and a certain comfort with uncertainty that not everyone could develop. The code was silent, yes, but also hidden, receding from direct observation whenever you tried to look too closely, revealing itself only indirectly through traces and artifacts and careful logical deduction. Debugging wasn't just finding errors, it was divining truth from incomplete evidence, a practice somewhere between engineering and mysticism. While programmers worked in the abstract realm of source code and logic, another group of specialists operated at a different level of the system, closer to the raw machinery, closer to the actual electrons and magnetic states that constituted computing at its most fundamental level. These were the computer operators, the people who sat at the console in the climate-controlled computer room, who monitored the system's operation, who intervened when things went wrong, who controlled the machine in ways that were both powerful and largely invisible to everyone else. The operator's console was unlike any interface that most programmers or users ever saw. While terminals displayed text, characters, formatted output, the console showed the machine's internals, registers and memory contents, system status indicators, hardware states. And it displayed these in hexadecimal, the base 16 notation that was the native language of the computer's architecture. To an untrained observer, the console display was incomprehensible, a grid of numbers and letters that seemed to follow no recognizable pattern. But to a skilled operator, these cryptic displays conveyed precise information about what the machine was doing at the hardware level. You could see which instruction the processor was currently executing, what values were in the various registers, what state the I/O channels were in, what programs were loaded in memory, and where. This visibility enabled a form of intervention that was both powerful and dangerous. When a program hung, when the system seemed to be stuck, when something wasn't behaving as expected, operators didn't have to wait passively for the situation to resolve itself or for the system to crash. They could intervene directly, at the hardware level, making changes that would immediately affect the running system. Real-time intervention often required manually dialing memory addresses, quite literally. Some console panels had rotary switches or dials where you could select a specific memory address, then read or modify the contents at that location. You could examine what was stored in a particular part of memory, could see the actual binary patterns that represented code or data. And if you knew what you were doing, you could change those values, flipping bits, altering instructions, modifying data while the system was running. This was surgery on a living system, making changes to a computer's brain while it continued to operate. The potential for catastrophic mistakes was enormous. Change the wrong memory location, or change the right location to the wrong value, and you could crash the entire system, corrupting data, terminating all running programs, bringing all processing to a halt. But skilled operators could work miracles with these capabilities. A program stuck in an infinite loop might be unstuck by modifying a variable that controlled the loop condition. A batch job waiting for a resource that would never become available might be manually advanced past that wait state. A system approaching a critical limit might be temporarily stabilized by adjusting internal counters or buffer allocations. These interventions left minimal traces. The system logs might show that an operator had accessed the console, but they typically didn't record exactly what the operator had done, which memory locations had been examined, which values had been changed. The intervention would have effects, would change how the system behaved, but the cause of those behavioral changes would be invisible to anyone who didn't witness the operator's actions. Beyond direct memory manipulation, operators controlled the system through console scripts and startup procedures. These were sequences of commands that configured the system, that determined which components would be active, what parameters they would use, how resources would be allocated. Small changes to these console scripts could alter system behavior deeply and subtly. A parameter that controlled buffer pool sizes might be increased to improve performance, but could also change how memory was allocated to concurrent programs, potentially affecting their paging behavior. A setting that adjusted I/O channel priorities might speed up certain types of operations while slowing others. A configuration choice about how the operating system scheduled work might change the relative timing of concurrent processes, potentially exposing or hiding race conditions. These were not changes to application code. The programs themselves remained identical, their source code unchanged, their compiled executables unmodified. But the environment in which they ran had shifted, and that environmental shift could produce different behaviors, different performance characteristics, different patterns of success and failure. Startup and shutdown procedures, in particular, contained hidden control paths that could significantly affect the system. The sequence of operations performed when the system was initialized, which components were started in what order, what checks were performed, what recovery actions were taken for various detected conditions. All of this was encoded in procedures that operators followed, scripts they executed, decisions they made based on console displays and system responses. Different operators might perform startups slightly differently, making different choices at decision points, responding to ambiguous situations in different ways. The result would be systems that were configured slightly differently despite, ostensibly, following the same startup procedure. These subtle differences might not matter most of the time, but under specific workload conditions, or when particular combinations of programs ran concurrently, they could produce different behaviors. Console commands often provided no immediate feedback, at least not feedback that clearly confirmed what had happened or what effect the command had produced. You might enter a command to modify a system parameter or to initiate some operating system function. The console would acknowledge that the command had been received, perhaps with a brief message or a change in status indicators. But whether the command had actually accomplished what you intended, whether it had the expected effect on system behavior, might not be immediately apparent. Confirmation of what had actually happened would appear later in system logs, records of operating system activities that were written to files and that could be reviewed afterward. You might enter a command at 2 a.m. during a crisis, trying to resolve a problem. The immediate response wouldn't tell you whether your intervention had worked. You'd have to wait, watch the system's subsequent behavior, eventually review the logs to see what had actually occurred. This delayed feedback made console operations somewhat like piloting an aircraft through clouds. You made control inputs based on your understanding of the situation and your instruments, but you couldn't directly see the results of your actions. You had to infer from indirect indicators whether your inputs were having the desired effect, and only later, when you could review flight data recordings, would you have detailed confirmation of what had actually happened. The combination of powerful but poorly documented console capabilities, delayed feedback, and minimal logging of operator actions meant that system behavior could change without any application code modifications. Programmers might observe that their programs were behaving differently, running faster or slower, succeeding or failing in different scenarios, producing different results. But upon examination, the code hadn't changed. The programs were identical to previous versions that had behaved differently. The actual cause of the behavioral change might be an operator action, a parameter adjustment, a configuration change, a manual intervention during a previous crisis that had left the system in a slightly different state. But discovering this cause was difficult because the operator actions weren't always documented, weren't always understood by the operators themselves in terms of their full ramifications, weren't easily visible to programmers reviewing their code trying to understand changed behavior. This led to situations where users blamed applications for issues that were actually rooted in operations. A program would start failing or performing poorly. Users would complain to the application support team. Programmers would investigate, would analyze the code, would find nothing wrong. They might conclude that the user complaints were mistaken or exaggerated, that the program was working as designed. But the users were correct that something had changed, that behavior was different than it had been. The change just wasn't in the application layer, it was in the operational layer, in how the system was configured or managed, in some parameter or setting or environmental condition that operators had modified, perhaps necessarily to address some other issue, perhaps inadvertently as a side effect of some other action. Discovering the ReTech required communication across organizational boundaries that didn't always communicate well. Application staff and operations staff often worked in different departments, reported to different management chains, had different priorities and perspectives. Applications people understood the business logic, but might know little about operating system internals or console operations. Operations people understood the system infrastructure, but might know little about specific applications or business requirements. Problems that cross this boundary could persist for extended periods, with each side convinced the issue was the other's responsibility, neither having complete enough information to identify the true cause. Control over these systems felt distributed yet invisible, spread across multiple people and procedures and layers of the system, but not clearly documented or centrally coordinated. Programmers controlled application logic. Systems programmers controlled operating system configuration. Operators controlled runtime behavior and real-time interventions. Management controlled policies and procedures. But no single person or group had complete control or complete visibility. The system operated through the collective actions of many people, each working in their specialized domain, each making decisions based on partial information and local priorities. The overall behavior emerged from these distributed actions in ways that could be difficult to predict or understand. And to those who depended on the system, end users sitting at terminals, managers reviewing reports, customers whose data was being processed, the machine seemed to act autonomously, to have its own agency and will. The system would sometimes work one way, sometimes another, with no apparent cause for the variation. It would sometimes accept transactions quickly, sometimes slowly, with no visible change in user behavior to explain the difference. It would sometimes produce results that seemed inexplicable, that didn't match expectations based on the data input and the documented business rules. And when asked why, the only answer might be that the computer had done it, that this was what the system calculated, as if the machine itself had made a decision rather than executing logic that humans had programmed. This perception of machine autonomy wasn't entirely wrong. In a sense, the complexity of these systems had grown to the point where they did exhibit behavior that wasn't directly traceable to specific human intentions. The behavior emerged from interactions between code written by many programmers, operating system functions designed by other programmers, hardware characteristics determined by engineers, operational practices developed by operations staff, configuration choices made by administrators, all interacting in a running system processing real workloads under constantly varying conditions. No one had designed or intended the specific emergent behaviors. They arose from the system's complexity, from combinations of factors that no one had fully anticipated or analyzed. The machine was following instructions, executing the logic it had been given, but that logic was so complex, so distributed, so dependent on timing and state and environmental conditions that its behavior in specific situations could surprise even the experts who understood individual components. The operators, sitting at their consoles in the quiet hours, watching hexadecimal displays scroll past, entering commands whose full effects they might not completely understand, were intermediaries between the human world and the machine world. They translated between intentions and actions, between observations and interventions, between the abstract logic of programs and the concrete reality of hardware states. Their work was largely invisible to everyone else, noticed mainly when something went wrong, when a crisis required their intervention, when their expertise was needed to recover from a failure or to optimize performance or to investigate a mystery. The rest of the time, they kept the machine running, managed its operation, made the small adjustments and interventions that kept complex systems stable, their contributions unnoticed because successful operations were simply expected. But their hidden control, their real-time interventions, their console manipulations and startup procedures and parameter adjustments, these shaped how the systems behaved in ways that were powerful yet largely undocumented, visible primarily through their effects rather than through any direct record of the operator's actions. The mystery of the silent code was deepened by this layer of operational control, this realm where systems could be modified in running, where behavior could change without code changes, where the machine's state and configuration were managed through cryptic hexadecimal displays and console commands that left minimal traces, where human expertise intervened directly in the machine's operation in ways that were essential but largely invisible to those who depended on the results. The machine ran, seemingly autonomous, but guided by hidden hands, shaped by interventions that happened in the darkness of the computer room, at the console where hexadecimal made sense, and where touching the right memory address at the right moment could make the difference between system failure and continued operation. Beneath the operating system, beneath the application programs, beneath even the machine language instructions that programmers might occasionally examine in dumps and debuggers, there existed another layer of code, another level of logic that controlled the fundamental operation of the computer itself. This was microcode, and it represented a realm of computing that was almost completely invisible to programmers, yet profoundly affected how their programs executed. The IBM System /370, like other mainframes of its era, was built on a principle that separated the machine's external architecture, the instructions it appeared to execute, the behavior it presented to programmers, from its internal implementation. The instruction set that programmers worked with, the machine language commands that compiled programs were reduced to, these were not directly implemented in hardware. Instead, they were interpreted and executed by microcode, a layer of very low-level programming stored in special fast memory called control storage. When a System /370 booted up, one of the first operations it performed was loading microcode from storage into control storage. This microcode would then govern how the processor interpreted and executed the machine instructions that programs contained. Each instruction in the System /370 instruction set corresponded to a sequence of microcode operations that actually performed the work, moving data between registers, performing arithmetic operations, accessing memory, controlling I/O operations. This architecture provided flexibility. The same external instruction set could be implemented on different hardware with different microcode, allowing IBM to create machines with varying price and performance characteristics, that all ran the same programs. More significantly, it meant that the fundamental behavior of the machine could be modified by changing the microcode without any changes to the hardware itself. Field engineers, the technical specialists who maintain the hardware and who had privileged access to the system at the deepest levels, could update microcode. These updates might fix bugs in the microcode itself, might improve performance of certain operations, might add support for new features, or modify how edge cases were handled. The updates would be loaded into control storage, and from that moment forward, the machine would behave differently at the most fundamental level. But these microcode updates were often undocumented as far as application development teams were concerned. The field engineer would perform the update, would note it in hardware maintenance logs that the application teams might never see, would perhaps inform the system's programming staff if the update was significant. But the programmers writing COBOL applications, the analysts designing batch processes, the users entering data at terminals, they would have no idea that the fundamental operation of the machine had been altered. And in most cases, this didn't matter. Microcode updates were usually backward compatible, designed to maintain the same external behavior while fixing internal issues or improving performance. Programs that ran before the update would continue to run after it, producing the same results, behaving identically from the programmer's perspective. But sometimes, microcode updates would change behavior in subtle ways. Instruction timing might shift. An operation that previously took a certain number of machine cycles might now take more or fewer. Edge case behavior could change. The way the processor handled unusual combinations of instruction parameters, or how it responded to error conditions, or what happened when operations were performed on boundary cases like maximum or minimum values. Most of the time, programs didn't depend on these details. Most code worked within normal parameters, used instructions in straightforward ways, didn't encounter edge cases, or depend critically on precise timing. But some programs, perhaps through bugs in their logic, perhaps through unusual coding practices, perhaps just through unfortunate coincidence, did depend on these subtle behavioral details. When microcode changed, these programs would begin behaving differently. A program that had run successfully for months or years would suddenly start failing. Or it would produce different results, incorrect calculations, corrupted data. Or it would perform unpredictably, sometimes working and sometimes failing with no apparent pattern. The programmers responsible for these programs would be baffled. They would examine the code and find it unchanged. They would check the input data and find nothing unusual. They would review recent changes to related systems and find nothing that should affect their program. The code that was failing was identical to the code that had worked previously. The data it was processing was similar to data it had handled successfully countless times before. They would go through their standard debugging procedures, examining dumps, adding diagnostic output, testing with sample data. But these investigations would reveal nothing, because the problem wasn't in their code. The code was correct, was executing exactly the instructions it had always executed. What had changed was how those instructions were being executed, what the machine was actually doing when it encountered those particular instruction sequences. Without knowing about the microcode update, without understanding that the fundamental behavior of the hardware had shifted, programmers had no framework for understanding these failures. The problems seemed impossible, violations of everything they understood about how computers worked. The same code, the same data, different results. It made no sense in their mental model, where computation was deterministic, where the same inputs and the same program always produced the same outputs. Teams would begin to describe the software as haunted, a semi-serious acknowledgement that something mysterious was happening, that the problems seemed to have no rational explanation. The code would work on Tuesdays, but fail on Wednesdays. It would work in the test environment, but fail in production. It would work for some users, but not others, with no detectable differences in how they were using it. These haunted software stories would spread, becoming part of the institutional folklore. Programmers would develop superstitious-seeming practices, avoiding certain coding patterns, running programs at certain times, performing rituals of recompilation or recreation that sometimes seemed to help for reasons no one understood. The problems would eventually resolve, either because someone finally discovered the microcode connection, or because another microcode update fixed the issue, or because workload patterns changed in ways that avoided triggering the problem. The root causes of these mysterious failures lived below the operating system, in a realm that application programmers had no visibility into and limited understanding of. Most programmers never thought about microcode, had perhaps never even heard the term. Their mental model of the computer had layers, application code running on top of the operating system, which ran on the hardware. They understood that their high-level code was compiled into machine instructions, and they might occasionally look at those machine instructions when debugging difficult problems. But the idea that those machine instructions were themselves interpreted, that they weren't directly executed by hardware, but were instead carried out through another layer of even lower-level code, that this layer could be modified independently. This was beyond their awareness. And even for those who knew microcode existed, few understood its behavior, its quirks, its potential for creating the kinds of mysterious problems they were encountering. Systems programmers, the elite group who managed the operating system and understood the deeper technical details, might know more about microcode. But even they typically didn't have access to microcode listings or documentation, didn't have tools to examine or modify microcode, couldn't easily diagnose whether a problem was caused by microcode behavior. That knowledge resided with hardware specialists, with field engineers, with IBM's own development teams who created the microcode. This created a gap, a blind spot in the collective understanding of the system. Problems that originated at the microcode level would manifest as application failures, would be reported to application programmers, would be investigated using application-level debugging techniques that were fundamentally inadequate for finding the real cause. The investigation would stall, the problem would be worked around or tolerated, the underlying issue would remain unidentified. Over time, as these experiences accumulated, as programmers encountered more and more situations where programs behaved in ways that seemed to violate deterministic expectations, trust in deterministic execution began to erode. The simple mental model, that computers exactly followed their programming, that the same code and data always produced the same results, was revealed as incomplete. Computers did follow their programming exactly, but there were more layers of programming than most people realized, and those layers could interact in complex ways. A program executing correctly according to its own logic could still fail if the operating system had a bug. An operating system working correctly could still produce strange behavior if the microcode had issues. Microcode operating as designed could still cause problems if the hardware had intermittent faults. The actual behavior of a running program was determined by the intersection of all these layers: application code, compiler behavior, operating system functions, microcode execution, hardware operation. And each layer had its own potential for bugs, its own version updates, its own quirks and edge cases. Understanding what a program would actually do in production required understanding all these layers and their interactions, a requirement that exceeded what most programmers could reasonably accomplish. The system's true state became unknowable in any complete sense. You could know what your application code was supposed to do. You might know what version of the operating system was running, but did you know what microcode version was loaded? Did you know whether any hardware had intermittent issues that only manifested under specific workload conditions? Did you know whether any operator interventions had left the system in a slightly unusual configuration? Probably not. This information existed somewhere, in maintenance logs, in system generation records, in operators' notes, but it was scattered, not centrally documented, not easily accessible to people trying to understand program behavior. The complete state of the system, including all the layers from application down to hardware, was distributed across multiple documentation sources, multiple responsible teams, multiple levels of abstraction that rarely communicated comprehensively with each other. This unknowability was disturbing to people trained in the precision and determinism of computing. Mathematics was certain, logic was clear, algorithms were exact. Computers were supposed to embody this precision, to execute with perfect reliability and deterministic behavior. But the reality was messier, more contingent, more dependent on factors that were difficult to observe or control. The mystery of microcode was particularly troubling because it violated assumptions at such a fundamental level. If you couldn't trust that machine instructions meant what they were documented to mean, if the behavior of the most basic operations could change silently, then what could you trust? The ground itself seemed to shift. The foundation on which all computing was built revealed as less solid than it appeared. Field engineers doing their job, applying updates to fix bugs or improve performance, had no malicious intent. They were maintaining the system, keeping it running optimally, addressing known issues. But the side effects of their maintenance, the subtle behavioral changes that could cause mysterious application failures, rippled upward through layers of abstraction, ultimately affecting users and programmers who had no awareness of the underlying changes. This was the nature of complex systems, where actions at one level could have unexpected consequences at other levels, where the whole was more than the sum of its parts, where emergent behaviors arose from interactions that no single person fully understood or controlled. The silent code of the 1970s mainframe included not just the application programs and operating systems that people thought about, but also this deeper layer of microcode, invisible yet powerful, changing yet undocumented, fundamental to operation, yet mysterious to most who depended on it. The machine's behavior was determined by code at multiple levels, and the deepest levels were the most hidden, the most rarely examined, the most likely to change without announcement. In the quiet computer rooms, the machines executed microcode billions of times per second, interpreting the machine instructions that programmers thought of as the real code, translating high-level operations into the actual manipulation of registers and memory cells and I/O channels. This happened invisibly, automatically, reliably, most of the time. But when microcode changed, when its behavior shifted in subtle ways, the effects rippled upward, causing failures that seemed impossible, creating mysteries that resisted solution, eroding confidence in the deterministic nature of computation. The system ran, the code executed, but beneath the visible surface, in the hidden depths of control storage and microcode sequencing, the true complexity of these machines exceeded human ability to fully comprehend or predict. The mystery deepened with every layer, every level of abstraction that could change independently, every possible source of unexpected behavior. And microcode, invisible to most, poorly documented, rarely considered, represented perhaps the deepest layer of mystery in these inscrutable, powerful, essential machines. In the interconnected world of mainframe computing, where multiple applications shared the same data, the same resources, the same infrastructure, a peculiar form of coupling emerged. Dependencies between systems that were never formally documented, never explicitly designed, but that arose organically from practical decisions made by different teams working independently, often unaware of each other's existence. At the heart of many mainframe installations were shared system catalogs, centralized repositories of metadata that described the datasets, files, and resources available on the system. These catalogs contained information about where data resided, what format it used, what programs could access it, and crucially, they often contained fields that multiple applications would reference for their own purposes. The catalog might include a field indicating a dataset's creation date, or its last modification time, or various status flags and descriptive attributes. These fields were intended for specific purposes, helping operators manage storage, enabling backup procedures to determine what needed to be copied, allowing system utilities to perform housekeeping tasks. But in the pragmatic world of application development, where programmers needed to solve immediate problems with available tools, these catalog fields would sometimes be repurposed, used for purposes their original designers never intended. Perhaps a field meant to hold a brief description of a dataset would be used to store a processing priority code. Perhaps a field intended for administrative notes would be used to flag datasets that required special handling. One development team would discover that this field existed, that it was accessible to their programs, that it could serve their needs. They would begin using it, incorporating it into their application logic, depending on it to control program behavior or to communicate information between batch jobs. Their programs would work correctly, would function as intended, would become part of production operations. Meanwhile, another team working on a completely different application, perhaps in a different department, perhaps supporting different business functions, would independently make the same discovery. They would find the same catalog field, would see that it wasn't being used for anything critical, as far as they could tell, would begin using it for their own purposes. For a time, this might work. The two teams' uses of the field might not conflict. They might be processing different datasets, or operating at different times, or using the field in compatible ways. But eventually, a collision would occur. One team would repurpose the field, changing what they stored in it, or how they interpreted its contents. This change would be perfectly reasonable from their perspective. They were modifying their own application, changing how their own programs used this field that they'd been relying on. But the change would break the other team's jobs. Programs that had run successfully for months would suddenly fail, or would produce incorrect results, or would exhibit bizarre behavior. The failures would seem inexplicable because the affected team had made no changes to their code, had done nothing different in their operations. From their perspective, their programs should work exactly as they had previously. Investigating these failures was difficult because the dependency was undocumented and informal. There was no design specification saying that application A depended on a particular interpretation of a catalog field also used by application B. There were no interface contracts, no formal agreements about how shared resources would be used. The dependencies had emerged organically, through independent decisions by different teams, and existed only in the code itself, in the logic of programs that read and interpreted these shared fields. Discovering that a catalog field was the source of the problem required examining the failing programs to see what external data they referenced, then investigating whether that data had changed, then tracing who else might be modifying it, then finding the other team and understanding what they'd changed and why. This investigation might take days or weeks, following a trail of dependencies that existed nowhere except in the distributed logic of multiple applications. Even more subtle were the effects of embedded numeric table codes, values stored in database fields or configuration files that would silently reroute processing logic. A simple numeric code, a 1 or a 2 or a 3, might determine which algorithm a program used, which validation rules it applied, which downstream systems it sent results to. These codes were powerful control mechanisms, allowing behavior to be modified without changing program code. Need to handle a new type of transaction differently? Add a new code to the control table and update the programs to recognize it. Want to redirect certain processing to a new system? Change the routing code in the configuration. But the meaning of these codes, the logic they controlled, often lived primarily in the programs that interpreted them, not in any central documentation. A code of 3 might mean one thing to one program, something different to another, nothing at all to a third. Understanding what a particular code value would cause to happen required examining every program that might read that value, tracing through their logic to see how they would respond. Small changes to these data values could affect thousands of transactions. Modifying a single routing code in a control table might redirect an entire category of business operations to different processing logic, affecting how thousands of daily transactions were handled. The change itself would be trivial, editing one field in one record of a control table. But the consequences would ripple through the system in ways that might not be immediately apparent. Perhaps the new routing would work correctly for 95% of transactions, but would fail for the 5% that had some unusual characteristic. These failures might not be noticed immediately, might only become apparent days later when someone reviewed exception reports or when customers complained about incorrect processing. By then, connecting the failures back to the control table change would require investigation, understanding that correlation existed between the timing of the change and the start of the problems. Performance tuning of these systems relied heavily on arcane configuration parameters, settings buried in operating system configuration files, or database management system control blocks that governed how resources were allocated, how operations were prioritized, how the system managed its workload. These parameters had cryptic names, complex interdependencies, and effects that could be difficult to predict. A parameter controlling buffer pool size might seem like a simple performance knob. Make it larger to improve database performance. Make it smaller to conserve memory. But changing it would affect memory availability for other components, would influence paging behavior, might shift the balance of which operations got cached in memory versus which had to access disk, could alter timing relationships between concurrent processes. Systems programmers would tune these parameters carefully, making small adjustments, monitoring the effects, gradually optimizing the system for their particular workload. They would develop deep expertise in understanding how parameters interacted, how changes would propagate through the system, what side effects to watch for. But this expertise was specialized and fragile. A single tweak to a configuration parameter could introduce failures that hadn't existed before, or could eliminate problems that had been persistent for months, and the mechanisms by which these effects occurred might be understood by only a handful of people who had the depth of knowledge to trace the causal chains. Consider a scenario. The system has been experiencing occasional slowdowns during peak transaction periods. A systems programmer analyzes the situation and decides to adjust a parameter that controls how the operating system schedules I/O operations, hoping to better prioritize interactive work over batch processing. The change is made. The system is restarted with the new configuration. Initial testing shows improved response times. Success. But 2 days later, a different problem appears. A nightly batch job that has run reliably for years starts failing intermittently. Sometimes it completes successfully, sometimes it times out, sometimes it produces incorrect results. The failures seem random, with no pattern related to data volumes or concurrent workload. Eventually, after extensive investigation, someone realizes that the I/O scheduling change has altered timing relationships in ways that expose a race condition in the batch job. A subtle bug that had always existed, but that had never manifested under the previous timing characteristics. The old configuration had, by pure chance, happened to schedule operations in a sequence that avoided the race condition. The new configuration scheduled them differently, and now the race condition occasionally triggered. Behavior would shift without visible cause, at least without cause that was visible at the application level. Programs would run faster or slower, would succeed or fail under different conditions, would exhibit different patterns of resource usage, all because of configuration changes made by systems programmers working at a different level of the system, making modifications that weren't communicated to application teams, addressing issues that had nothing to do with the applications now experiencing changed behavior. Configuration became a form of programming, a way of controlling system behavior that was just as powerful as writing code, but that operated through different mechanisms. Setting the right parameter values, choosing the correct table codes, arranging the configuration files properly. These activities determined how the system would behave just as surely as the actual program logic did. But this configuration programming was less visible than code, less formally managed, less subject to the development disciplines of testing and documentation and change control. Configuration changes might be made by operators following procedures, or by systems programmers responding to performance issues, or by administrators updating control tables to reflect new business requirements. These changes would go into effect immediately or at the next system restart, without the compilation and testing cycles that code changes required. Logic lived outside source code, embedded in database tables, in configuration files, in operating system parameters, in catalog fields, in the complex web of settings and values that govern system behavior. You could examine an application's source code exhaustively, could understand every line, could trace every execution path, and still not fully understand how the application would actually behave in production, because so much of its behavior was determined by external factors. Configuration settings it read, control tables it queried, system parameters that affected its resource allocation and timing. This externalization of logic had practical advantages. It allowed behavior to be modified without recompiling programs, enabled operational flexibility, permitted different configurations for development, test, and production environments. But it also meant that understanding system behavior required looking beyond code, required examining configurations and data and settings that might be scattered across many different repositories, managed by different teams, documented in different ways, or not documented at all. The mystery of the shared resources was the mystery of emergent complexity, of systems that had grown organically through the independent actions of many people over many years, each solving their immediate problems in reasonable ways, but collectively creating a tangled web of dependencies and interactions that no one fully understood. The mainframe sat at the center of it all, executing programs written by dozens of teams, processing data shared across hundreds of applications, operating according to configurations that reflected accumulated decisions of countless administrators and operators and systems programmers. The machine ran deterministically, following the instructions it had been given, but those instructions came from so many sources, existed in so many forms, interacted in so many ways that the overall behavior became unpredictable, mysterious, knowable only through observation and experience rather than through analysis and deduction. A change in one place would ripple outward in ways that might not be anticipated, affecting systems that seemed unrelated, creating failures that seemed impossible to explain. The connections existed, the dependencies were real, but they were hidden in the intricate details of how different components happened to use shared resources, how different programs happened to interpret common data, how configuration parameters happened to affect multiple aspects of system behavior. The silent code executed in an environment where logic was distributed, where behavior was controlled by more than just program instructions, where the true determinants of what would happen in any given situation included not only the code, but also the configuration, the data, the shared resources, the accumulated state of systems that had been running continuously, evolving gradually, for years. Understanding required not just reading code, but understanding the entire context in which that code operated. And that context was too large, too complex, too distributed across too many systems and teams and documentation sources for any individual to fully comprehend. The mystery deepened with every shared resource, every undocumented dependency, every piece of logic that lived outside the source code in the hidden spaces of configuration and data. As we reach the final movements of our journey through the mysterious world of 1970s mainframe computing, we encounter perhaps the most haunting aspect of these systems: the way they handled time itself, operating on rhythms that extended far beyond the daily cycles we've discussed, into patterns measured in months and seasons, creating problems that appeared and disappeared like ghosts, manifesting only under rare alignments of circumstance that might occur just a few times each year. Some institutions ran critical jobs only monthly or quarterly, batch processes that executed not nightly, but on longer cycles aligned with business calendars. Month-end closing procedures would run on the last day of each month. Quarterly reports would be generated every 3 months. Annual reconciliations would happen once per year. These were essential processes handling critical business functions: financial reporting, regulatory compliance, inventory reconciliation, tax calculations. But their infrequency created unique challenges. A program that ran only 12 times per year had limited opportunities to fail, limited chances to reveal bugs. During development and testing, these programs might be run dozens of times, tested thoroughly with sample data. They would work correctly, would be promoted to production, would run successfully the first month, the second month, perhaps for many months or even years. Then, under some particular combination of circumstances, a specific data pattern that only occurred occasionally, a particular alignment of month-end date with day of week, a workload condition that rarely manifested, the program would fail. It would encounter a bug that had existed in the code since it was written, but that had never been triggered before because the specific conditions necessary to expose it had never occurred. This created what some programmers began to call a seasonal haunting effect. A job would fail in March but run successfully in April, May, and June. Then it would fail again in July. The pattern might correlate with something. Perhaps months with 31 days versus months with 30 or 28. Perhaps the specific day of the week that month-end fell on. Perhaps business cycles that created different data volumes or distributions in different months. Discovering these patterns required observation over extended periods. A bug that manifested only in months with 31 days would need at least a year's worth of history to identify the pattern with confidence. During that time, the program would fail intermittently, would be investigated after each failure, would be rerun successfully, because reruns often happen days later when the temporal conditions had changed, would be marked as an intermittent problem of unknown cause. The infrequency made debugging extraordinarily difficult. You couldn't easily experiment, couldn't make a change and quickly test whether it fixed the problem. You made a change, waited a month to see if the next run succeeded, and if it failed again, waited another month to try a different fix. A bug that in a daily program might be resolved in a week could take many months to fix in a monthly program, with each iteration requiring a full monthly cycle to validate. Compounding these challenges were the sophisticated journaling and recovery mechanisms that mainframe systems employed. These were designed to protect data integrity, to enable recovery from failures, to allow systems to continue operating even when problems occurred. Database management systems would maintain journals, logs of all changes made to data, allowing transactions to be rolled back if errors were detected, allowing the database to be restored to a consistent state after crashes. These recovery mechanisms were powerful and generally beneficial. They protected against data loss, enabled quick recovery from many types of failures, provided audit trails for compliance and debugging. But they also had a side effect. They masked many application errors, made mistakes less visible, allowed problems to be corrected automatically without clear indication that anything had gone wrong. Consider a program with a bug that caused it to update the wrong record in a database. Without recovery mechanisms, this would corrupt data, would create obvious problems that would be quickly detected. But with transaction journaling, if the program later encountered an error and terminated abnormally, the entire transaction would be rolled back, undoing the incorrect update along with everything else the program had done. The database would be left in its original state, as if the program had never run. From a data integrity perspective, this was exactly right. The buggy program's partial, incorrect changes were undone, preventing corruption. But from a debugging perspective, it made the problem invisible. The program failed, yes, but it left no trace of the incorrect update it had attempted. The error that was the real problem, updating the wrong record, was hidden behind the more visible error that caused the program to terminate. The system appeared to silently fix mistakes, to protect against errors through mechanisms that operated automatically, invisibly, without explicit acknowledgement of what they'd prevented. Users would submit transactions that would partially execute, encounter errors, be rolled back automatically. The user might see a message indicating the transaction failed, but they wouldn't see what had gone wrong internally, what data had almost been corrupted, what complex recovery operations had executed to restore consistency. This protective layer created distance between users and the system's actual operation. Users experienced acceptance or rejection of their inputs, success or failure of their requests, but without detailed explanation of the internal processes that had led to those outcomes. A transaction would be rejected, and the user would see a message: "Transaction failed. Please retry or contact support." But why did it fail? What specifically went wrong? What would retrying accomplish? Explanations for these mysteries required consulting manuals and experts, resources that weren't always readily available or accessible. The manuals themselves were often dense technical documents, hundreds or thousands of pages covering system behavior in exhaustive detail, but organized in ways that made finding specific information difficult. You needed to know what you were looking for, needed to understand the terminology, needed to have enough background knowledge to navigate the documentation effectively. Experts, the senior programmers, the systems administrators, the technical specialists who had deep knowledge of the systems, were valuable resources, but finite ones. They could be consulted, could provide explanations, could help interpret error messages and system behaviors. But they had limited time, were often busy with their own responsibilities, couldn't provide detailed explanations to everyone who encountered confusing system behavior. So in the absence of clear explanations, in the gaps between documented behavior and observed reality, folklore developed. Users and less experienced programmers would develop their own theories about how the system worked, explanations that were partly true, partly misconception, partly speculation. These folk theories would be shared, would become part of institutional knowledge, would guide how people interacted with the systems. Always submit your request before 10 a.m. for best results. Was this based on actual system behavior related to daily workload patterns, or was it superstition? If you get that error message, just wait an hour and try again. Was the delay necessary for some technical reason? Or was it just giving time for transient conditions to clear? Or was it entirely unnecessary, but had become accepted practice? These folk explanations served a purpose. They allowed people to operate effectively without complete understanding, provided practical guidance that often worked even if the underlying reasoning was questionable. But they also represented a loss of clarity, acceptance that complete understanding wasn't achievable, that the systems would remain partially mysterious, and that the best approach was to learn what seemed to work through experience and shared knowledge, rather than through systematic study. The mainframe culture of the 1970s valued stability over clarity, reliability over transparency. The highest priority was keeping systems running, maintaining continuous operations, protecting data integrity. If achieving that stability meant accepting some opacity, some mystery in how the systems actually worked, that was a price worth paying. Documentation might be incomplete, but the systems ran reliably. Internal behaviors might be cryptic, but the essential business functions were performed correctly. Users might not fully understand the machines, but they learned how to work with them effectively. The culture adapted to the technology rather than demanding that technology fully explain itself. The code spoke rarely and cryptically, communicating primarily through terse error messages, through numeric codes that required manual lookup to interpret, through behavior that revealed its logic only indirectly. Programs didn't explain what they were doing or why. They didn't provide detailed status updates or offer insights into their decision-making processes. They accepted input, performed processing invisibly, produced output or error messages. The internal journey from input to output remained hidden, knowable only to those who had written the code or who were willing to invest substantial effort in studying it. This taciturnity wasn't hostility or deliberate obscurity. It was a natural consequence of the constraints under which these systems operated. Producing explanatory output consumed resources, slowed processing, increased costs. The systems were designed to maximize efficiency, to process the maximum workload with available resources. User-friendly explanations and detailed status reporting were luxuries that the resource-constrained environment couldn't easily afford. And so an entire era of computing developed around these powerful but opaque machines, systems that handled critical functions while remaining mysterious to most who depended on them. Organizations built their operations on foundations they didn't fully understand, trusted processes they couldn't completely explain, accepted outcomes produced by logic that lived in silent code. This era cemented the myth of powerful, silent machines shaping outcomes unseen, a perception of computing that would influence how people thought about technology for decades to come. The image of the mainframe, the massive computer in its climate-controlled room, attended by specialized operators, running programs written in arcane languages, processing data through complex logic that few could fully comprehend, became the archetype of computing power. These machines were portrayed as objective, authoritative, infallible. The computer calculated, and its calculations were trusted above human judgment. The computer processed transactions, and its processing defined what was true. If the computer said your account balance was a certain amount, that was your balance. If the computer approved or denied your credit application, that was the decision. The machine had spoken, cryptically perhaps, but definitively. This trust was partly warranted. The systems were generally reliable, usually accurate, carefully maintained. But it was also partly mythological, overlooking the complexities we've explored throughout this journey. The silent data corruption, the mysterious bugs, the undocumented dependencies, the configuration changes that altered behavior, the microcode updates that shifted fundamental operation, the seasonal hauntings and ghost bugs, and all the ways these systems could behave in unexpected, inexplicable ways. The myth of the silent, powerful machine served social and organizational purposes. It simplified understanding, provided a clear authority to defer to, enabled decisions to be made efficiently without endless debate about computational details. The computer says, became a conversation ender, a final authority that settled disputes and defined reality. But beneath that myth was a more complex reality. Systems that were powerful, yes, but also fragile in subtle ways, reliable overall but fallible in specific circumstances, silent not because they had nothing to say, but because they lacked mechanisms for saying it, mysterious not by design, but because their complexity exceeded human capacity for complete understanding. As we conclude this exploration of mainframe computing in the 1970s, we're left with a picture of an era when computation became essential to modern society, while remaining largely incomprehensible to most people who depended on it. The machines hummed in their climate-controlled rooms, processing billions of instructions, handling millions of transactions, shaping economic and social outcomes through the execution of code that few could read and fewer still could fully understand. The programmers who worked with these systems developed specialized expertise, learned to debug in darkness, to trust incomplete information, to work within constraints that would seem impossible to later generations. The operators who managed the machines mastered cryptic console interfaces, intervened in running systems at the hardware level, kept operations flowing through knowledge that was largely unwritten and impossible to fully transfer. The users who depended on these systems adapted to their rhythms and their mysteries, learned what worked through experience, developed folk knowledge to navigate the opacity, accepted that the machines would sometimes behave in ways that seemed inexplicable, but that were presumably logical if you understood the hidden depths. And the silent code executed, night after night, year after year, processing the essential work of commerce and government and industry, mostly reliable, occasionally mysterious, always powerful, shaping a world that was becoming increasingly dependent on computational systems that were becoming increasingly complex, increasingly opaque, increasingly impossible for any individual to fully comprehend. This was the era that established patterns of trust in computational authority, of acceptance of technological opacity, of specialized expertise concentrated in small groups, of systems that worked without being fully understood, patterns that would persist long after these specific mainframes were retired, long after the technology evolved to new architectures and approaches. The myth of the silent, powerful machine was born in these climate-controlled rooms, in the green glow of terminal screens, in the cryptic hexadecimal of console displays, in the mysterious behavior of code that seemed to know when it was being watched. And though the technology has changed, though modern systems operate differently in many ways, echoes of that myth, that relationship between humans and inscrutably complex computational systems, remain with us still. The code was silent, yes, but it spoke volumes through its silence, through the mysteries it created, through the trust it demanded and usually deserved, through the complexity it embodied that exceeded human comprehension, yet somehow, mostly worked. This was computing in the 1970s, powerful, essential, mysterious, and quietly transformative, processing the digital foundations of a modern world through mechanisms that would remain, to most who depended on them, forever inscrutable. The machines ran, the code executed, the work was done, and the mystery endured, a legacy of an era when computing power first became truly central to society, while remaining, fundamentally, silent and unknowable.